Hey everybody, Mr. Brown here, and this presentation is for Chapter 13 from Klein's Organic Chemistry, which covers ethers, epoxides, and thiols. We will focus mainly on the ethers, epoxides side of this chapter, cover their nomenclature and reactions. We may mention the thiols, but they will not be part of the test or anything like that. So our focus again are just on the ethers and epoxides from Chapter 13. So to begin, we take a look at what the ether group structure looks like. An ether group is a group that includes an oxygen atom that is bonded to two alkyl chains. The R groups can be alkyl, aryl, or vinyl groups. So, if there's double bonds or benzene rings and stuff like that, that's fine. Notice the big exception here is no acyl groups, no carbons double bonded to oxygen right next to the sp3 oxygen, because that's a separate group entirely known as an ester. We've talked about those, or probably heard about those. So those are not ethers, is kind of one of the big examples there to keep in mind if you see that double bonded oxygen beside the O's. Of course, we won't run into any like that in our practice, but we do want to point it out. There are some natural examples of ethers given in the box below. We can see some pretty well-known compounds. Melatonin, something our bodies produce, morphine and vitamin E that we get from natural sources, have ether groups included in their molecules, and quite a lot of biological molecules exhibit ether groups within them. Those are just some common examples. Now we will discuss the nomenclature as it relates to the ether part of the chapter. There's kind of two schools of thought when it comes to naming ethers. If you've got to name an ether as a side group in a larger molecule, we'll probably default to the IUPAC naming for ethers. And when you encounter an ether in a larger molecule, it's always going to be considered a side group. It's never going to be part of the parent chain, and there is no ending that we apply to a molecule to designate it an ether in it. So it's just always a side group, and it's named based on how many carbons that side group contains as it pertains to regular IUPAC naming. And you can see the common names for IUPAC names rather, for the ether side groups that we will encounter in this chapter. If it's one carbon, it's a methoxy group. If it's two carbons, it's an ethoxy group. You can also have the other groups listed there: propoxy, isopropoxy, etc. And I've got a few examples here on this slide. The first one there, of course, in blue, we see that would be considered a methoxy group. Here on this next molecule, I've got a couple of methoxy groups right here because they contain just one carbon on the other side of the oxygen from this structure that would be considered the parent chain in this molecule. And then we've got a little bit more complex. So this would be an isopropoxy side group because of the isopropyl structure of the alkyl chain on the other side of the oxygen from the main chain of the compound. And then finally, this structure here, this would actually be the main chain because ethers are always side groups. And so this 4-carbon oxygen with the oxygen structure here, that would be a butoxy group. So that's to demonstrate that ethers are always side groups in their molecules. They're named according to how many carbons are on the other side, or part of the side chain, if you will. For our smaller ethers, much like the analogs of acetylene, we can often name or it's often used as a common name to name the side groups on either side of the ether, and then just put the word ether behind the name, indicating that we're dealing with a small ether with a couple of alkyl chains on either side. And you will run into this a lot because ethers are very often used as solvents in reactions. Diethyl ether may be one of the most common organic chemistry reaction solvents. So we would be remiss if we didn't mention the common naming scheme that is often employed with ethers. The big thing to keep in mind here is to be technically correct when you list the side chain of each, or list the side group of each alkyl chain in these smaller ethers. Make sure that you are putting them in alphabetical order according to the IUPAC alphabetization rules concerning the prefixes and all. So that's how we name smaller ethers, and when we talk about smaller ethers, especially in the context of using them as solvents in the lab, they will more often than not be referred to with their common naming system. We have some nomenclature examples here, and we will name these molecules both with an IUPAC name and the common name where applicable, and I believe that may be only in the first molecule here. So we'll take the first one into consideration, and we see we have a couple of alkyl side chains bonded to an oxygen there in the middle. So this is one of those smaller ethers that would more than likely be named with the common naming system. And we see that one side is an ethyl group and the other side is an isopropyl group. Ethyl comes before isopropyl in the alphabetization scheme, so this molecule in the common naming system would be called ethyl isopropyl ether. But if we want to name it by the IUPAC naming scheme, we need to find the longest unbroken carbon chain that doesn't contain the side group, and in this case that will be the propyl chain that we see here. And if this is the propyl chain, then the ethoxy group that we find here is on the number 2 carbon. So the IUPAC name for this molecule would be 2-ethoxy propane. Moving on to the second example down here, since we have the halogen in there, I'm probably going to steer away from naming this with a common name. And I also noticed that the halogen has stereochemistry, so I probably need a stereochemistry designator at the front of this molecule. Luckily for us, the H is already on a dash, so if we number this one 1, the long chain would be 2, and the methyl group would be 3. That's going to give us a counterclockwise S configuration. And the longest unbroken chain of carbons is 1, 2, 3. But that would put our locants as number 2 and 3. So if we go the other way, our locants become 1 and 2 instead. So 1, this is still 2, and 3 carbon. So we can see we have an ethoxy group on carbon 1, a chloro group on carbon 2, and chloro is going to come before ethoxy in alphabetization. So this is going to be 2, rather S, 2 chloro, 1 ethoxy propane. So now we will move down to the last molecule we have down here, and we see that the parent chain in this molecule is just going to be the benzene ring. So this is going to be a substituted benzene naming structure. We would put, to get the lowest locants, we could put this as 1, 2, and 3. Any other order, or any other, that would be 3 and that would be 4 rather. Any other ordering of those structures would put us in larger locants, so that would be the correct numbering structure for this ring. So this would be 2, 4 dichloro, 1-ethoxy benzene. So those are the examples that we're giving for the ether naming schemes, ether nomenclature schemes. I'm sure you'll see a lot more practice as you move through your assignments. Cyclic ethers are also a common motif seen in many natural molecules, so we would be remiss if we didn't mention those. We're going to focus on one in particular, but we will highlight the names of some of the common ones here. For cyclic ethers, there is a naming scheme for them, and the size of the ring containing the oxygen determines the name of the molecule, if it is a parent name. And we see that for a 3-member ring, 2 carbons and 1 oxygen, we call that oxyrane. For 4 members, oxetane, 5 oxalane, and for the 6-member ring system, we call that oxane. And those are, like I said, those are common motifs, common structures throughout many biological molecules. So I wanted to mention them here. The rest of the chapter focuses on the 3-member ring system, the oxyrane, and we have a different name for those because they're so common. We also call them epoxides, and you may have heard the word epoxide before as it relates to different maybe commercial products, especially a lot of paints and glues have these epoxide structures in them and may be called something like an epoxy or epoxide type varnish or paint or something like that. We're going to focus on those and talk about how those are named in the upcoming parts of the chapter, but I did want to highlight the very common cyclic ethers seen throughout organic chemistry. So here we see the naming scheme for our epoxides, and again, these are these 3-atom ether rings with 2 carbons and 1 oxygen. When we're dealing with oxyrane rings that have small substituents on the side, we're going to name that as a substituted oxyrane, with oxyrane being the parent name of the chain. When you're doing this, this is somewhat awkward. We don't see this very often, but when we use this naming scheme, we're going to use the oxygen atom as locant number 1, and then the 2 carbon atoms are going to be 2 and 3. The more substituted carbon atom should be number 2, with number 3 being the less substituted or not substituted at all carbon in some cases. In larger molecules, when there's a much better choice for a parent chain, say a long alkyl chain or something like that, oxyranes are going to be named as epoxide side groups, and the locants of both bonded carbons need to be given. So you see the example here. We have a pentane, a 5-carbon chain, as the choice for the parent chain, and that puts the legs, if you will, of the epoxy group on number 2 and 3. So we're going to call that 2,3 epoxy. We also have an ethyl group on 3, 2,3 epoxy, 3-ethyl 2-methyl pentane. We'll see some examples of these on the upcoming slide. Moving on to the last example, we are going to try to name our molecule down here both as a substituted oxyrane and as an alkyl chain, but again, or rather this time, we see there is some stereochemistry involved. So the first thing I may do is try to figure out what the stereochemistry of this molecule comes out to, whether it's R or S. And if I'm doing that, then I may want to come over here in the side taking our last example into consideration. The first thing we notice there is some stereochemistry involved, and we are going to have to try to determine if this is an R or an S version of this molecule. So I would probably start there, maybe over here in the side somewhere. Redraw the chiral carbon in the same configuration. There we go, and then try to assign some priority to each of these groups. Looks like the top one here bonded directly to the O would probably be group number 1, and then this carbon here has bonds to C, O, and H. This carbon This carbon here has bonds to C and C, and this carbon here has bonds to C, or rather H, H, and H. So it does appear that our number 4 priority is already on the dash, thankfully, and this would be group number 2, this would be group number 3. So this looks like an R version of this molecule with that clockwise rotation. So now I'm really equipped or ready to handle answering what the name of this guy is. If it's a substituted oxyurane system, oxygen is number 1. This is the more substituted position as number 2. So we would see a 2-methyl 2-phenyl, and M comes before P in the alphabet. I had to think about that one. LMNOP. So we would name this one 2-methyl 2-phenyl oxyrane. And finally, if we're naming this as, and that is R, by the way. And finally, if we're naming this as an alkyl chain, we would probably number this as carbons 1, 2, and 3. So we have a propane chain here with a couple of substituents. It has a 1,2-ethoxy R, 1,2-epoxy rather, not ethoxy, R, 1,2-epoxy, 2-phenyl propane. And those are our examples for naming epoxides. I'm sure you will have more practice to work on your own. I hope these help. Going forward, naming epoxides both as substituted oxyuranes and as epoxy groups on alkyl chains. Let's take a look at some of the ether characteristics or characteristics of these ethers that we want you to be familiar with and be able to explain a little bit about. So the oxygen in ether groups is sp3 hybridized, so it has 4 sp3 orbitals, and it will have tetrahedral or close to tetrahedral geometry. Notice, unlike an alcohol, which has the hydrogen, which allows it to be both a hydrogen donor, acceptor, and donor, the hydrogen itself allows it to do the hydrogen bonding. There is no hydrogen in the ethers, and so therefore they do have the very negative region of space around the lone pairs near the oxygen, and that can accept hydrogen bonds from other compounds, but an ether by itself is not able to hydrogen bond. So some of that polarity does lead to higher boiling points than our analog alkyl chains, as you can see in the diagram there. But due to the lack of actual hydrogen bonding like we see with our alcohols, we're not going to get very high boiling points. And so they kind of sit in between the commiserate alkyl chains versus the alcohols as far as boiling point goes. You can see propane, plain old propane down there, boils at negative 42 degrees Celsius, while dimethyl ether, where we've replaced one of the carbons, that middle carbon, with an oxygen atom, rather to give the ether, and the boiling point goes up by about 20 degrees Celsius. But once you get hydrogen bonding involved, you know, the chief of all intermolecular interactions, that the boiling point jumps up by about another 100 degrees. So you can really kind of see the strength of hydrogen bonding in the alcohols there. And then finally, this highly electronegative region of space around those oxygens, lone pairs, make ether great reaction solvents. We see ethers used a lot throughout organic chemistry for two reasons, really. We can engineer them such the alkyl chains will allow us to dissolve nonpolar substances rather well, but the lone pairs on the oxygens gives us access to be able to dissolve polar substances, so we can dissolve ions into organic solutions and have them react with all of the reactions that we've been looking at so far, quite frankly. The other side of that, though, is that they are liquids at room temperature, but they are usually very highly volatile, especially specifically something like diethyl ether, which we work with a lot, boils at like 40 degrees Celsius. So you can easily remove that solvent from that reaction when you're done, because it boils so low, and recover your final product. So the lone pairs around the oxygen in ethers give us access to desirable characteristics of ethers without the hydrogen bonding seen in alcohols. A particular class of ethers that's gained a lot of prevalence in the organic laboratory, and one I want you to be aware of, are compounds known as crown ethers. So you buy these from the chemical supplier when you have to dissolve highly ionic substances into low polarity solvents in order to get them to react. These structures that you see here, these are liquids that you buy, but these molecules are engineered specifically to hold onto the metal cation part of ionic compounds and so-called host that cation, so the anion is free to react. We'll take a look at a couple of those on the next few slides and a little bit more in depth. So when you're choosing your crown ether to buy, you have to match the size of the ring up to the ion that you want to capture. For example, 18 crown 6 is the ideal size to trap a potassium cation. So if you're putting, for example, some potassium fluoride into some nonpolar solvent, you would use crown ether to stabilize the potassium ion, allowing the fluoride ion to be free and move about the cabin to react, if you will. This is kind of what crown ethers were designed to do and what they're engineered to do, and they're used an awful lot. So I think that's why we make a point to talk about them in this ether chapter. Again, they're used to help ionic salts needed for organic reactions to dissolve in low polarity solvents. Those metal ions really prohibit us from dissolving things like sodium chloride, for instance, directly into a nonpolar solvent. So crown ethers can help that process along, so when we want to dissolve these things in nonpolar solvents, they will. Here's a diagram that kind of shows how that happens. Something like benzene is a very good example. Benzene does not dissolve potassium fluoride at all, really. It has a minuscule solubility, but if we dissolve our potassium fluoride in some crown ether first, we can then dump the crown ether potassium fluoride solution into our benzene, where we have our other reagents dissolved as well, and then we have fluoride ions available to go and bond in other places. So really all we want you to learn here or know here is what they're used for. They're used to help highly polar ionic compounds dissolve in low polar solvents, and the choice of the matter, or what you have to be able to do, is pick the correct size crown ether for the corresponding metal cation that you're using. And we give you the list here. You can see the small 12 crown 4 molecule solvates lithium ions, the medium size 15 crown 5 solvates sodium ions, and the larger 18 crown 6 solvates potassium ions. And we know from their positions on the periodic table that ion size increases as you move down those periods. So we have lithium, sodium, potassium in order, smallest, biggest to largest. As I said earlier, ethers are very important solvents in organic chemistry. They are commercially important products, with thousands of tons being produced millions of tons really, produced on a yearly basis. Industrially, we can prepare large amounts of ethers by dehydration of ethanol, and you can see the mechanism for that here. All you have to do is put some ethanol in acidic solution and heat to 130 degrees Celsius. And the following proton transfer, SN2 process proton transfer, results in the ethanol being converted to diethyl ether, which can then be distilled and bottled and sold. In the laboratory, there is a well-known ether preparation called a Williamson ether prep. So this is an easily worked up process for the laboratory. If you want to make, say, a unique small ether for some kind of reaction, this is the process that you would take, something you want to design and maybe kind of difficult to find on the market or something like that. So this is used in the laboratory for making unique ethers. Symmetrical as well as asymmetric ethers can be prepared by deprotonating an alcohol with a strong base like sodium hydride and then treating that with an alkyl halide. So an alkyl halide will substitute with the resulting alkoxide ion, giving us an ether product. This is an SN2 concerted process, so if there is stereochemistry, we do expect inversion. And one point of note is that we can only use our primary alkyl halides for this process. So the alcohol group is going to have to be the one that contains the side chains and stuff that you want, because you can only basically add primary alkyl halides to these alcohols. We'll look at a couple of these examples as we move forward. Here on this slide, we can see an example of what we mean of a demonstration of we have to use primary alkyl halides to afford ether products that we want. We have here two proposed routes for forming methyl tert butyl ether from an alcohol and treatment with a strong base and alkyl halide. In the first example, we take tert butanol and we deprotonate it with sodium hydride, and then methyl iodide is substituted, affording the methyl tert butyl ether. That is a well-proposed process because the methyl iodide, is a primary alkyl halide. The bottom reaction shows methanol being treated with the sodium hydride. So we're deprotonating methanol and then trying to substitute a tert butyl iodide molecule in at that position. And we have learned, and it's been done experimentally, just shown that this is not a thermodynamically favorable reaction. So the reaction really just doesn't take place because that is not a primary alkyl halide. So we must use, when we're proposing Williamson ether synthesis, we must be cognizant of using a primary alkyl halide, not a secondary or a tertiary. So on this slide, we are asked to propose a Williamson ether synthesis to provide each of the molecules shown below, and I'm going to show you how I would approach these questions. So we know that we need to have some alcohol plus some alkyl halide to yield our ether, and each of the R groups will come from here and here. And so if we're thinking about which alkyl halide we would need and which alcohol we would need, I would first start by disconnecting those bonds there and see what the resulting alkyl halides look like to see which one gave me, or if both gave me, a primary alkyl halide. So on this side, the left side here, breaking that bond and turning that into an alkyl halide gives us a secondary alkyl halide, it looks like. However, breaking that bond on that end does give us the primary alkyl halide reactant that we probably need to force this reaction to carry forward. So I will propose the Williamson ether synthesis of a cyclohexyl sec-butyl ether to start with a cyclohexanol being deprotonated and treated with this primary alkyl halide, And it should result in the expected ether that we have drawn. Now in the second example, we see that we have a ether that has a cyclohexane with a methyl group on one side and then just a plain methyl group on the other side. So if I were to break the bonds here and the bonds here, I would see that this structure here would probably give me a tertiary alkyl halide. The methyl group on the other side, however, has no problem replacing one of its hydrogens and being a methyl halide, which is actually more ready to react than any other alkyl halide. So I would definitely say the alcohol that is going to be necessary for this prep is going to be this tertiary alcohol here. Treat it with a strong base to deprotonate it, and then give me a methyl bromide to give me the SN2 process that's going to afford that molecule there. And how about this final molecule here? How can we provide this molecule with maybe just one simple starting point? If you notice, I have a ring in this molecule. So if I draw something with just a alcohol on one end and an alkyl halide on the other end, maybe something like this. So this is the alcohol side here. I severed this bond here and I made this an alcohol, and then we're going to have 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons there. Here in our final example, an astute observer might recognize that there's a possibility we could make this molecule from just one starting material. If we sever this bond in the ring here, and we put a halogen there instead, that would be a primary alkyl halide. We could turn this into an alcohol, and just by simple treatment with NaH, we would expect this to be our product. So let's see if we can draw that. We have the alcohol here on one end, leading to a carbon with a couple of methyl groups. Moving down, we have a carbon here. Moving here, we have another carbon. Moving here, we have another carbon. That one does have a methyl group on it, followed by a last carbon bonded to a halogen. Then, if we just throw that in a reaction vessel with some sodium hydride, we should expect the product we have listed. These are examples of how we prep simple ethers, unique ethers in the laboratory via the Williamson ether synthesis. Another route to ether synthesis is alkoxymercuration, just like we saw with preparation of alcohols. So we learned back in chapter 8 that if we take an alkene and treat it with mercury acetate followed by water and some reductant such as sodium borohydride, then we get a hydration of the alkene and we get a hydroxyl group or an alcohol group added to the Markovnikov side of the double bond, and because we use the alkoxymercuration, we don't have to worry about any carbocation rearrangement. Similarly, alkoxymercuration, demercuration, the same process can be used to make ethers, except this time we replace the water with another alcohol. And so when instead of adding OH to one side of the bond, we add OR to the Markovnikov side of the double bond, giving us some designed ether. Here we see our examples for identifying reagents that we could use to prepare each of the following via the alkoxymercuration demercuration process. These are pretty straightforward questions. We know that we want to add an ethanol to the Markovnikov side of the double bond in this case. So the reagents we would use would be HgOAc, the mercury 2 acetate, and we would need to use ETOH to put the O ethanol in on that molecule. That is always followed by a reductant, NaBH4. And those would be the reactants we would need. Specifically, that ethanol is kind of what we're looking for there. And so in the next case, we can see we're adding a oxygen followed by a cyclobutane group. So the alcohol we're going to need there is cyclobutanol. So if we were writing that out, we might write it HgOAc2 with, I might withdraw a cyclobutanol there, followed by our reductant NaBH4. The next two questions ask us how we would do alkoxymercurations preparing some symmetrical ethers using cyclopentene and propene as our only source of carbon. I want you to work on those on your own, and I want to discuss those in class together. I think those are really fun questions, and they kind of test your ability to apply a few things learned this far in organic chemistry. So we will circle back to those in class together at a later time. Here we take a look at the reactions of ethers that we are going to concern ourselves with, and there's really only one of those, and that is acidic cleavage. So when you treat an ether with HBr, HI, or HCl, you see the result is a replacement of that oxygen atom on both sides of the ether with the applied halogen. And so you really kind of get, you get two products if you're not using a symmetrical ether. If phenyl is cleaved, then you do get phenol as one of your products. So that's one way you can design your reactions to be helpful. Both cleavages will involve SN2 substitutions with the alkyl, with the halogen rather, and so you should expect any applicable inversions in stereochemistry. So we see some examples here on this slide of acidic cleavage questions, and we're going to try to predict the products here. In the first example, we see a very symmetric ether, so that's only going to give us one product. So we're going to remove the oxygen essentially and replace it, substitute it, if you will, with the bromine. So we should expect that product. In the second example, we have a cyclic ether, so each end is going to be halogenated, and the resulting structure will look like this. We should have 4 carbons, so that's 1, 2, 3, 4 carbons with a halogen. I did that wrong because those are iodines on either end. In the next example, we do see a phenol R group and an ethyl R group, so we should expect an ethyl bromide as one of our products. And we learned that the sp2 centers are not good candidates for substitution, so instead it's the protonated version of the resulting R group, and so we get phenol as one of our products. In the third example, if we break that bond there, again we would have substitution at an sp2 center, so that's probably not going to happen. So we're going to form phenol there. If we break off that bond there, we do just have an alkyl chain. It remains connected to our parent molecule, so the products for that reaction are going to be, we're going to have a phenol group in this position, and then here we're going to have that cleaved from the ring now, and there is 1, 2, 3 carbons in that chain, 1, 2, 3 carbons in that chain, and we're going to replace the oxygen with the iodine from the HI. I'm going to erase that to give myself a little bit more room and move on to the next question, example D here. So we're going to break this bond here and break this bond here and replace with the iodines. However, in this case we can see a stereocenter, so we would maybe expect inversion at this stereocenter. However, we'll notice that this is going to form a tertiary, or this is a tertiary R group. This carbon here is tertiary. So this one is going to prefer an SN1 process versus an SN2 process, and that's going to allow the iodine ion to substitute from either face, and so we'll end up with a racemic mixture of products in this one. So we do have that carbon there, and it's going to have an iodine bonded to it, and then it will have the propyl group, the propyl group on it, as well as a methyl group, and we'll draw that without any stereochemistry designation to show that it will be a racemic mixture. And then beyond that, there's going to be 1, 2, 3, 4 more carbons. 1, 2, 3, 4 more carbons, and then we will also substitute an iodine on the other side. In the final example, we'll pull this to the top up here. In the final example, we have a little bit simpler problem this time. We're just going to remove the oxygen and replace with BRs in both cases. So those are examples of acidic cleavage problems of ethers with HX. Here we are going to take a look at the final reaction that we are going to study from the ethers and epoxides chapter, and that is how the epoxides are prepared in the laboratory. So alkenes, double bonded carbons inside molecules, can be converted into epoxides. We can replace a pi bond with the cyclic 3-member ether by treating the pi bond with something known as MCPBA, which stands for metachloroperoxybenzoic acid, and you can see that structure here. So we just buy that stuff from the chemical supply, and we treat any alkene with this MCPBA, and it does what we are saying it does. It replaces the pi bond with the oxyrane ring. It's important to keep in mind that due to the mechanism of this reaction, substituents that are cis to each other in the starting alkene are going to remain cis to each other in the epoxide, and subsequently substituents that are trans to each other in the starting alkene are going to remain trans to each other in the finished epoxide. Halohydrins can be converted into epoxides also upon treatment with a strong base. However, you get the same stereochemical outcome, so there's really no reason to prefer one reagent over the other, rather than MCPBA is a little bit easier to handle than something like elemental bromine or chlorine. So you probably will just try to use MCPBA if possible to convert an alkene into an epoxide, but we'll look at the result of both in the examples. And so for our final thought, we will take a look at how to prepare the following epoxides, try to figure out what starting product we're going to combine with MCPBA to get the following examples. And when I do these, I like to just draw out my double bond, so I know the double bond is going to replace the epoxy ring here. So I'm going to draw that as a double bond, and then I'll see what's on either side of that double bond. So we have a methyl group and a phenyl group sharing one side, so I will put those up. That would be my methyl group here. And I will draw a phenyl group there. And then we also have another phenyl group and a hydrogen sharing another side of the molecule. So that should be the molecule that we combine with MCPBA to afford the product that we see in example 1. So then it follows in example 2 here, we are going to draw a double bond. One side is going to have a methyl group and a hydrogen. Sharing the side with the methyl group is another hydrogen, and sharing the side with the hydrogen is a cyclohexyl group. Treat that with MCPBA, and we should afford the intended product. In the next example, we see a ring structure. So if I draw my double bond like this, I see that I have a hydrogen pointing to the back, so I'll put him up, and then a methyl pointing to the front, so I'll put him down. And then the other side is still going to connect to itself, but on the side with the hydrogen, I have a 2-carbon chain, so I'll do 1, 2, actually just 1 carbon there before I meet the oxygen. And then on the bottom side, I should have 2 carbons, 1, 2, before I meet the oxygen. So the structure that we look, would be drawn something more like this. We might turn it up on its side there. Draw 1, 2, 1 directly to and then a methyl group. So it may look something like that. It's actually kind of a poor drawing. We'll exit out and leave it alone like we have it over here. That is a good representation of the molecule that we would need to treat with MCPBA to afford the intended product. And then finally, we might bring this guy over here to give us some room. What would the starting material look like? So if we draw the double bond first, we can see that one leg moves down and starts to actually connect with the other leg on the other side of the molecule. And then if we put a hydrogen up right here, we can see, so there should be a second carbon, a third carbon, a fourth carbon. So we've made our way here. 1, 2, 3, 4, 5 carbons along the way. 1, 2, 3, 4. Put our 5th carbon there maybe along the way. And one more. Then we would have just a plain hydrogen on this side. So maybe cleaning that up a little bit. Our starting material would look something like that for treatment with MCPBA to give us that following epoxide. So that's going to wrap up the reactions and practice that we're going to focus on for the ethers and epoxides chapter. As always, if there's anything you would like me to answer or help you with concerning this material, please shoot me an email, brownb@sandhills.edu. Thanks.